So we will learn today about cyclic groups. Cyclic groups, a very important concept in algebra. We will start with a cyclic subgroup generated by some element A in the group. This is the notation. So we start with some element A in the group G, and then we generate a subgroup using this element A. This subgroup consists of all powers of A to power 0, which is the identity, A to power 1, which is 1 itself, then A square, which means we make the operation between A itself, and then we get an element, and then we add it there, A to power 3, and so on, A inverse square, A inverse to power 3, and so on. And this is, let me rewrite it here in case it's small. This is A to power n, so all integer powers of A. And we will call this a cyclic group generated, cyclic subgroup generated by A. We need to prove it is a subgroup indeed, and this is what we do in theorem 7.14. Before we start, let us have some illustration by doing some examples. Let us assume that our group G is Z8, and assume we want to choose an element A, which is 2. Now let's see. In here, when we say Z8 and we don't mention the operation, and we are assuming that Z8 is a group, then that means the operation is addition, modulo 8, not multiplication, because this is not a group under multiplication. So the operation here is addition. So the subgroup generated by 2 will consist of powers of 2, all powers, integer powers. But here notice that a power of 2 is adding 2 to itself. Let me write it here. A power 2 to power n means 2 plus 2 plus 2 n times. This is 2 to power n. We agreed in such a notation. Any element inside a group raised to some integer power means you take that element and make operation with itself n times. Okay? So let us complete this. Now this will equals 2 to power 0, which is the identity. 2 to power 0 here means I add 2 to itself 0 times, right? Remember what I said here. So we get the 0. 2 to the power 1 is 1. Sorry, 2 to the power 1 is, okay, what is that? 2 to the power 1 is 2. What did I say? Okay, sorry. 2 to the power 2 is 4. It is 2 plus 2. 2 to the power 3 is 2 plus 2 and plus 2, which gives 6. 2 to the power 4 is 8, so it is 0. I think I said 2 to the power 4 already. So let me just make sure, because I think I said something different what I wrote. This is 2 to the power 0. This is 2 to the power 1. Here I wanted to say 2 square. I think I said 2 to the power 4. And here 2 to the power 3. Okay? And then 2 to the power 4 is 0 again. 2 to the power 5 is 2, because that is 2 added to itself 5 times, which is 10, modulo 8 is 2. 2 to the power 6 is 4, and so on. So this is the cyclic subgroup generated by 2. Let me write that. This is the cyclic subgroup generated by 2, but we are working here inside Z8. Okay, now if you go and find the cyclic subgroup generated by 2 in Z7, and what that would be equal. Let's do it. Let's do it together. So let me go here and say now what we want to do. Find the cyclic subgroup of 2 in Z sub 7, and here Z sub 7 including the 0. Here I am assuming the operation is addition, because Z7 is not a group under multiplication because it contains 0, does not have inverse. So let's go. Okay, 2 to power 0 is 0. 2 to power 1 is 2. 2 to power 2 is 4. 2 to power 3 is 6. That's 2 plus 2 plus 2. 2 to power 4, which is 8, which is 1, modulo 7. I mean 2 plus 2 plus 2 plus 2, 4 times. Okay. 2 to power 5, which is 10, modulo 7 is 3. 2 to power 6, which is 12, modulo 7, 5. 2 to power 7, which is 14, modulo 7, 0. And then we come here, and then we are done. And actually, this gives us the whole group C7. Good? Okay. Let me do one more example. Find the cyclic group generated by 3 in C7. Now here star, I am specifying the operation now. Okay? Okay. First we go 3 to power 0. That means I multiplied 3 with itself 0 times, which is 1. 3 to power 0 is 1. 3 to power 3 is 3. 3 square, that's 9. Modulo 7 is 2. Now here I am multiplying 3. 3 square here means 3 times 3, because we are working with multiplication. Okay. So 3 square is 2. 3 to power 3 is 27. Modulo 7 is what? 6, right? 3 to power 4. So that will be 3 times 6, 18. So that will be 4. So make sure. And 3 to power 5 will be 5. 3 to power 6 will be 3, and then we are done. Okay? So to make sure to let you later look at it, this is okay, this was 3 to power okay, this is okay, let me write all of them. This is 3 to power 0, 3 to power 1, 3 to power 2, 3 to power 3, 3 to power 4, and 3 to power, did I miss something? 1, 0, 5. Okay, I missed nothing. Okay. Now we have an idea how to start with an element. Okay. How to start with an element and generate a subgroup out of it. And this subgroup generated this way is called cyclic subgroup. Okay, so now again we have an idea. If we have an element in some group then take all powers of that element, then we generate a subgroup called cyclic subgroup generated by that element. And let me here explain why it is called cyclic. Okay, so I will go over the example we just have worked out. Let's go back to this example here. Now, 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. Now, 2 to the power 4 is 2 plus 2 plus 2 plus 2, which is 8. Modulo 8 is 0. So we went to this again. 2 to the power 5 is 2. Then we are here. 2 to the power 6. Then it is 4. 2 to the power 8. Then it is 6. Now continue. 2 to the power 7. So this is 7. 2 to the power 8. And then we will go to 0. 2 to the power 9. Then we go to 2. So we will keep cycling. Okay? So taking all the powers of 2 will make us keep cycling over these elements. 0, 2, 4, 6. Same thing will happen here. So this was 2 to the power 0, 1, 2, 3, 4, 5, 6. So this is 2 to the power 6. Now take 2 to the power 7, you will get here. 2 to the power 8 here. 2 to the power 9, 2 to the power 10, 2 to the power 11, 2 to the power 12, 13, and then 14 again here. 15, 16, 2 to the power 17, 18, and 19, and so on. So this is why we call it cyclic, out of cycle. Same thing, play with that thing. 3 to the power 6, this will be 3 to the power 6, this is 3 to the power 7, and so on. Play with it so that you have a feel of what's going on. And this is the reason why we call it cyclic. So good, now we have an idea. We have an idea. Again, start with a group, any group. Take an element. From that element, take all powers according to the operation. Okay? And these powers will give you cyclic group. Subgroup generated by A. In the examples I demonstrated, the cyclic subgroups were all of them finite. Sometimes it might not be finite, and we will see. So this is the idea. One element generated a subgroup, which is called cyclic group generated by A. Now, we said it is a subgroup again and again, but we did not prove it. And the proof is easy. And this theorem does that for us. If G is a group, and then choose an element and take this thing, and then we have a subgroup. Now, to prove that a set is a subgroup, we need to prove two things. It is closed under the operation, and for every element in there, the inverse lives in there too. So let us choose two elements from this set. Let's call them B and C. Belongs to this set. This means every element in here is some power of A, right? So B have to be some power of A to power R, and C must be some other power, A to power S, for some integers R and S belonging to Z. Now multiply them. Multiply B times C, it is A times R, A times S, which is A times R plus S, and plus R plus S is an integer. So this is an integer power of A, and it is one of the elements that are in there, and then we are done. So the multiplication is this way. Now let's assume we have an element in here, and we want to show the inverse. Let us assume that we want to show the inverse of B, and B takes that form. Now note A to power negative R belongs to this set, right? Because this set with this parentheses contains all powers of A, positive or negative. Okay, so if p equals a to power r, then a to power negative r, we have it there, and b times a to power negative r is a to power r, which is b, a to negative r, which is a to power 0. A to power 0 is the identity. A to power 0 is not 1. It is 1 only in the case that 1 is the identity, which is the multiplicative identity. But if we have addition operation, the addition, then a to power 0 is 0, not 1, okay? So this is the identity, whatever it is. And so what we prove that P inverse, which is the above element here, belongs to this. So we have done. So we have done it. So this is a subgroup of G. So we proved two things. Okay. Good. The examples we have just seen when we worked with Z7 and computed the cyclic subgroup generated by do2 with addition, we noticed that the cyclic group generated by 2 gave the whole C7. And same thing when we worked with Z7 star, the non-zero element in Z7, and computed the subgroup generated by 3, we found that this subgroup contains the whole group. So sometimes it happens that when the group comes out to be generated by one element, then we will say that G is cyclic. What I just said a little while ago, that Z7, to emphasize here with addition, is generated by 2. So I will say Z7 is cyclic. And also we saw that the non-zero element of Z7, the units in there, with multiplication, is generated by 3. So I will say this is cyclic group and this is cyclic group. The whole group generated by one element. In other words, the subgroup generated by that element is the whole group. Okay, and here is an example. Let's go to U15, the units, the set of units or the group of units inside Z15, and compute the subgroup generated by 7 and see if that gives the whole group. Let's go for it. And now the operation here is 7 to power 4 again. This is 7 to power 5. This is 7 to power 6, 7 to power 7, and so on. So we are done. Okay. Okay, good. Now let's do the group generated by 13. So we need, okay, this one shall be easier. What do you think? The group generated by 13 is 13 to power 0 is 1. Okay, 13 square. I will not say 13 square. I will say negative 2 square. Because 13 and negative 2 are the same element in Z15. So negative 2 square is 4. Some cyclic groups. Okay. Okay, correct? Good. Thank you, Asma. Okay, let's move to the theorem after. Oops. Let's see what this says. G is a group and we have an element A in G. Okay. Now it says if A has infinite order, then the subgroup generated, the cyclic subgroup generated by A is infinite subgroup. And it consists of all elements A to power K, where K belongs to Z. Okay, how we prove that theorem? We already learned some theorem before, which I don't, the number of that theorem. It says that if the order of K of A is infinite, order of A is infinite, then we get A to power K, A to power K are all distinct. Do you remember that? That theorem. And because of that, this part is true. What happened with us with the examples before, we have seen that keep taking the powers will go over cycle, will repeat the elements again and again, which means 2 powers of A can be the same. That is because the order of A was finite. If the order of A is infinite, then this will not happen. No 2 powers will be the same. All powers will be distinct. That means the set generated by A will be infinite. Okay. Now, the second part of the theorem says that if A has a finite order, which is n, then the subgroup generated by A, the cyclic subgroup, has order n. And the elements consist of the identity, A itself, A square, A to power 3, all the way to A to power n minus 1. And then if we keep taking powers for A, then we will go over this element again and again. And the proof of this theorem depends in a theorem that we have already seen, which says that assuming A has order n, then A to power I equals A to power j, if and only if, this is important theorem, I and j are equal modulo n. Oops. I and j are equal modulo n. Okay? And we remember that theorem, correct? So now any power, so the proof of part 2, any power A to power k, for k is any integer, must equal to A to power I for some I between 0 and n minus 1. Why is that? Because k is congruent to 1 of the integers 0, 1, 2 all the way to n minus 1, congruent modulo n. Okay, so modulo n, if you take any element k, then that k will be congruent to the remainder of it after dividing by n. Do you remember that theorem? So any integer k is congruent to one of these integers that represents any possible remainder after dividing by n. So any element will be in the cyclic group will be one of these. Now, if you go back to the examples we had just worked out, and you will see that the number of elements in each one of these examples actually equals the order of the generator. If I go back to here, then the number of elements in this one, it has 4 elements. That's because order of 7 is 4 inside U15. And same thing in here. It has 4 elements. The same number as order of 13, which is 4. This is 4. And go back to the above examples that we have done and find out about the order of the cyclic subgroup generated by 2 or 3 in Z7 or in Z8. Okay. Now this theorem is just a duplicating of the theorem we have just seen, just for the case if we have addition, not multiplication. If we have addition, then instead of a to power k, we will say k times a. Okay? A to power k, when we have multiplication, means a times a times a times a. When we have addition, it means a plus a plus a plus a, which is k times a. and the elements will be 0, which is a to power 0 here, the identity is 0. A to power 1, which means one copy of a to power 2, which means a plus a to power 3, which means a, plus a, and so on. Okay. Now we will see these are the examples where I want to show that groups are cyclic. Now we can see when we say Z is a group, that means we are dealing with addition, because Z is not a group under multiplication. So it is generated by 1. That means it is K times 1, where K belongs to Z. This is under the definition. And this is itself Z. So we will add 1 to itself 0 times, that give us the 0, or 1 time, or 2 times give us 2, or 3 times give us 3, or minus 1 times, which will give us minus 1, and so on. Okay, this is Zn, and same thing, Zn is generated by 1. For example, let's take 1 belongs to Z6. Then 0 times 1 is 0, 0, 2, 3. Just we keep adding 5, 2, 3, 4, 5, and then 6, which is 0 again, and so on. So any group of this form and this form, these are cyclic groups. Cyclic groups. Any one of these. But I want to emphasize it for this one and for this one, and we will need it later. Okay, now let's see. L, we have seen this group before, consisting of 1, negative 1, I, and negative I. It's generated by I only. Is that true? Now the operation here is multiplication. So I to power 0 is the identity, which is 1. I to power 1, which is I itself. I square, which is negative 1. I to power 3, which is I square times I, is I. I to power 4, which gives us 1, and then we are done. Okay. Oh, okay. We have done this already. Right? So Z7 star generated by 3. Okay, great. A very important theorem here says if we have a group which is cyclic, then any subgroup inside it is also cyclic. And the proof is interesting. Okay? So it says every subgroup of cyclic group is cyclic. Every subgroup of cyclic group is itself cyclic. So let's go for the proof. We start with a group which is cyclic, call it G. So we have a cyclic subgroup, cyclic group called G, and we are saying it is cyclic, so it is generated by one element. Let's call it A, the generator. So it is generated by A. And assume H is a subgroup of G. Now we want to prove H is cyclic. So we are assuming it is a subgroup. The theorem says every subgroup is cyclic. So our goal here is to prove that H is cyclic. Okay. Now, it starts the following way. It says if H consists of the identity, then we have nothing to do. Then it is cyclic. This is so trivial. Assume H is not the identity. That means there is an element in A which is not the identity. So H contains a non-identity element. Okay? Which is, this is what I wanted to say. A sub I belong to H. And A sub I, okay, let me write it here maybe. A sub I belong to H. And A sub I does not equal the identity. This is what I wanted to say, which means I is not 0. This is what we are saying here. Okay. So we have H subgroup of G, and we got in hand an element inside it which has the form A to power I. Fine? Good. Now, A to power I is in H, and H is a subgroup. So the inverse of A to power I must be in H, because H is a subgroup. So here we go. A inverse is in H. The inverse of AI, or A to power minus I, is in H, since H is a subgroup. Okay, now having this and this in hand, we can assume that H contains an element which takes the form A to power positive. If I is positive, then this is fine. If I is negative, then minus I is positive. So either AI or A to negative I, either I or negative I is positive. So we get some element, C, K. We will choose K to be the smallest positive. So before we say that, we guaranteed that A contains some positive powers of A. We said either I or negative I is positive. So we have that thing in hand. Now we will choose the smallest positive powers of A that lives in H. Here we go. And we called it K. And this is the smallest positive powers of A that lives in H. Good? Okay. Remember, we want to show that H is cyclic. So we want to get in hand an element from inside H that generates the whole subgroup H. Got it? And this element now is in hand. It is A to power K in H, where K is the smallest positive integer. And now our goal is to show that H is generated by A to power K. What do we mean H is generated by A to power K? It means that if we take, this is H, and A power K lives inside. If we take any other element inside H, then that other element must be some power of A to power K. In this way, this other element is generated by A to power K. So we raise A to power K to some power, and then we obtain that one. And this one is arbitrary element in H. Then that happens for every element in H. So H is generated by A sub K. Okay? Let's do that. So let us assume that other element I talked about, let's call it small h. And show that small h is some power of A to power K. Okay. So here we go. Choose arbitrary element in H, small h. Then that originally comes from G, correct? Because H lives inside G. And now G is generated by A. So every element inside G is some power of A. So H equals A to power M. This is M for some M. Fine? Good. Now we have H equals A to power M. So we have M fixed. And we already have K fixed. They are two fixed integers. What we are going to do now, divide M by K. Good? Divide M by K. This is M divided by K. The result is Q, and the remainder is R. And you know the remainder must be less than the divisor and greater than or equal 0. Okay? Now let's see what happened. R equals M minus QK. From here we get that. Good? Now what we get here? A to power R, I'm not sure if these powers are clear. Let me make it a little bigger. A to power R. Hopefully this is better now. Okay. A to power R. Now let's replace R by this. M minus K times Q. Rewrite them. A to power M. A to power minus KQ. Rewrite them again. This is M. Okay. And this is that. Let's see what happened. Now A to power M is in H. Why? It is a small h. So it belongs to H. A to power K, we chose it from H. So it belongs to H. So what happened? This and this belongs to H. A to power K belongs to H. So its inverse belongs to H. So its inverse raised to power Q belongs to H. All that belongs to H. But all this now belongs to H. But this is A to power R. Now we got A to power R belongs to H. Now something happened here. Let me make it smaller. A to power R belongs to H. Remember, what is the smallest power of A that lives inside H? Is K. The smallest power that lives inside power of A that live inside H is K. And we are saying here K is less than R is less than K, and A to power R lives inside H. So this is a contradiction unless what? R equals 0. Correct? So we cannot allow R to be less than K and A to power R to belong to H. So we have to force R to equal 0. And once R is 0, we go back to A to power M. So A to power M, what is M? If R is 0, go back to here. If R is 0, what is M? M is K times Q. So A to power M is A to power K times Q. Okay. So this is what I said. A to power M is what? Is H. So H is a power of A to power K. Correct? So H belongs to the subgroup generated by A to power K. And we have achieved what we wanted. We chose an arbitrary element in capital H, and we proved it is a power of A to power K. Okay? And that indeed means, and this means H is generated by A to power K. And so H is cyclic. Okay. The very last thing in today's lecture is to show that some groups are not cyclic, but they can be generated by two elements. Okay. So we have seen groups, cyclic groups, that are each one of them is generated by one element. But D4, for example, cannot be generated by one element. Now, using the multiplication table in D4, we can show that any element in D4, R1 is power of R1, R2 is R1 square, R3 is R1 to power 3, and R0 is R1 to power 4. So R0, R1, R2, R3 could be obtained as powers of R1. Now for the remaining element, H is contained from itself. Now T can be contained using H and R1. V can be obtained using H and R1 again, but squaring R1. D can be obtained using H and R1, but to power 3. So using R1 and H with different powers, and operation here is composition. So I compose some power of R1 with some power of H, and power means either 0 or some positive power. Then doing so, I can obtain the whole group D4. So I will say D4 is generated by R1 H. And I will write here that D4, so it might be good to see it this way, D4 can be obtained using R1 to some power, say K, and then compose that with H to some power T, okay, such that K equals either 0 or 1 or 2 or 3, T equals 0 or 1. And then if we do so, substitute for this K any of these values, and for T any of these values. T takes 0 or 1 only, K takes 0, 1, 2, 3, and then do all these computations. That will produce D4. And the table here is to see how this computation goes for quick. Like if I want to compute R1 to power 3 and then compose it H and then compose it with R1 to power 3, so I need to compute R1 to power 3. So this is R1 square, right? This is R1 with R1. Now to compute R to power 3, I go to R2 and take it with R1 again. So this is R1 square with R1. This is R to power 3, which is R3. Now R3 here, I compose it with H. So H compose R3. I will go the other way, H, then R3. So I will go H above there. So I will erase that, because we start with H first here. So I will go H, okay, then R3. As compose R3 gives D. I believe I did it the opposite way last lecture, maybe. Just make sure. Okay, so therefore D4 is generated by two elements. And that's it for today. We're done. Thank you.